Hope you had a good weekend. So last week we spent a lot of time discussing how we can go from a purified biological specimen to high-resolution, high-quality micrographs. And now we're going to start talking about how we can go from those micrographs to three-dimensional structures. And the beginning of that will be Sjors discussing image refinement.
Thank you, Chris. Yeah, so the purpose of today's lecture is to give a little bit of insight what goes on inside the computer programs when we actually align our images either in 2D class averages or in 3D reconstruction. And this lecture is not really intended to give you practical insights on all the kind of steps that you need to do in the workflow. That will be tomorrow's lecture by Rafa. Today's lecture will be a bit the theoretical background of what happens inside the program, hopefully taking away some of the things that might seem a bit magic otherwise. So I'll start with a very intuitive introduction, and then we'll go into the detail of alignment of images. How do we get them all into register? We'll compare what approaches have been taken in the field in the past. Then we'll expand the alignment problem to classification as well and include 3D reconstruction there as well. And then at the end, I'll discuss how things are more convenient to do in Fourier spaces. And Paula last week already introduced you to some of the important concepts there. So the intuitive introduction, I will use my favorite object again. This is Jan. The slides are now almost a decade old, so I apologize, but I think they're still quite effective. So he'll go to secondary school next year. Chris already discussed the microscope, and so did Christos. But basically, Laurie explained us how we have a little shallow swimming pool full of Jans who swim around. There's many copies of Jan, and they swim around all kind of different orientations, go inside this high vacuum machine, and then we shoot electrons through them. And then already it was discussed by Paula last week that what you get is like a true two-dimensional projection of all the integrated density, as provided that Jan is sufficiently thin that it's a weak phase object. So you get something that looks like an X-ray projection in the hospital, but now for scattering potential inside your molecules. Now, because these pictures are rather ugly, I'll use black and white photographs to kind of illustrate two-dimensional projections of the 3D object, which will be in color. So that's our first problem, is that we're going to collect images in 2 dimensions, whereas what we're really interested in is the 3-dimensional structure of these objects. Okay. Now there's some other inconveniences, and these were all covered last week. I'll just briefly repeat them. So the whole system, the microscope, is imperfect, and we also need to defocus to get contrast, and that leads to artifacts in the images, and these are then described by this contrast transfer function that Paula discussed. So if this would be a true projection of Jan, then a CTF convolved image would look like this. So some things that are black become white, and some things that are white become black. Overall, the contrast in the image reduces, so you get a kind of this grayish-like image. Now, and then on top of that, it was discussed last week as well that Jan is extremely sensitive to the radiation that we use to image, and therefore we have to use very few electrons to put on him. And that then leads to large amounts of noise in the images as well. So we now have thousands of copies of Jan, and provided they're all projections of the same 3-dimensional object of Jan, then hopefully we can combine these all together. The different 2-dimensional views will provide complementary information in 3D, and averaging over many thousands of them will reduce the large amounts of noise here. Good. So fortunately, we had these many copies of Jan, and they were all swimming around in different orientations. So now how do we go from many 2D projections in different orientations to one 3-dimensional reconstruction? And we use a process called projection matching. This has been in the field for many years. And we start from some initial 3-dimensional guess of our object, and I'll come back to that in a while on how we could get there. Okay, but provided we know that Jan is kind of a puppet, then we can make a 3-dimensional puppet in the computer, and then what we do in the computer, we generate what we call reference projections. So in all possible orientations in the in the three-dimensional space, we make projections. So we have some top views and some front views and some side views, etc. And then we have all these experimental projections, and I've taken away the noise so you can see what's going on. And we're going to compare, and we'll come back to what that means, compare. We're going to compare whichever of these reference projections fits best with the experimental image. And that could, for example, be, this is a top view, but slightly from the side. Okay? Now, because we have many, many thousands of these projections in many different orientations, we can repeat this process for all of them. So now all two-dimensional images have been assigned an orientation relative to this three-dimensional reference object. And then we can use that complementarity that different 2D views provide of a 3D object, and our brain kind of does that the whole day. We have two eyes and we move around, so we get two-dimensional images on our eyes, but our brain reconstructs in 3D. We'll get back to a more mathematically satisfying explanation later. But we can then do a reconstruction of all these images of Jan. Now, what goes in the reconstruction are only that. They are images of Jan. There is nothing to do with, the images have nothing to do anymore with this orange puppet that we started with. Yet, the reconstruction that comes out is somewhat of a mixture of the two. And that is because all the orientations that we have assigned were based on comparisons with the orange reference projections. And because the images were so noisy, we now make all these orientations are slightly wrong, and they're wrong in a systematic manner that tries to reproduce the orange puppet. And that's the kind of the template bias, and people have called it Einstein from noise as well yesterday. But hopefully what we get out is somewhat more like a real reconstruction of Jan than we started off with. And then we can repeat the process. So we can now again project this three-dimensional model that we have in all possible orientations, see which ones fit best, and hopefully now we will reduce the overall errors in the alignment, and we'll get a reconstruction where the influence of the orange puppet is reduced, and then hopefully we can do this until some kind of convergence point where we get a true 3D reconstruction of Jan. So this kind of iterative refinement process can serve to remove template bias. It also, you can do computational tricks because searching the entire space of three-dimensional orientations can be very expensive. So you can start off doing this relatively coarsely and then go finer, etc., and thereby just save computational speed. Those are two reasons why we want to do this in an iterative manner. Now, that brings us then to the question, how do you actually compare two images and or how do you match them together? So if you have this whole library of two-dimensional computer-generated reference projections, and I have a whole set of two-dimensional images, how do I bring those in the register and decide whether that first one was the actual top view of Jan slightly from the side? Okay, so that brings us to something which in math they call an incomplete data problem, and that's how you could consider alignment of EM images against a reference. And you could think of it as a problem where part of the data was not observed or experimentally. And in this case, this is these orientations of all the individual images, of all the individual projections of Jan. Now, as a structural biologist, we're not really interested in those orientations. What we're really interested in is in the three-dimensional reconstruction of Jan. So they're kind of a nuisance that somehow that we paid £5 million for a microscope, and it doesn't even tell us what the relative orientations of all the images were. If that microscope would exist and you get the relative orientation of every particle printed next to it, then this whole problem of image refinement didn't exist. Okay? So because it's incomplete, it becomes difficult to solve. Often people use iterative methods, and then this perfect microscope, which would tell you, then the whole thing would be very easy and we wouldn't have a problem at all. Okay, now incomplete data problems are all around in science, and for the crystallographers in the audience, another very famous one is the phase problem in X-ray diffraction, so where you only measure intensities of the Fourier components and all the phases get lost. So how you deal with the kind of problem, as you'll see, is actually very similar. Now, let's first go to let's forget 3D YANs and so on and go to a much simpler test case to study alignment of images. And these are now noisy images of a penguin. It's a two-dimensional signal we're after here, and they're all different rotation, in-plane rotation. They're actually all nicely centered. So the only kind of nuisance parameter that we have here is the in-plane rotation of the images. So these are the observed images, and now this missing data, the incomplete part of the data, are the in-plane rotations. Now, if we want to get an estimate, as good estimate as we can of the underlying signal, of the two-dimensional penguin image, then that is not completely straightforward how we should do that from this set of images. If they all were to be aligned, because we had somehow had access to this missing part of the data, which were the relative orientations, then it would be much easier, because then we could just add them all together and kind of calculate the average would be our best possible guess for the underlying signal of the noisy data set. Okay, so that would be easy. Now, what do you do in case of an incomplete data problem? And in the field of electron microscopy, but also in the field of X-ray crystallography, for those of you who are more familiar with that, there have been two different options. And the first option is to add the missing information to the model. So rather than saying, okay, all I'm interested in is how that two-dimensional penguin looks like, you're going to say, I'm also interested now in finding the relative orientation of all the individual particles. And the other option is to put this in a statistical framework where we calculate a probability of observing each of the individual noisy penguin images, regardless of whatever orientation it is in. And in mathematical terms, that's done by an integration over all these missing parameters, which are the rotations. So we're going to calculate a probability of observing an experimental penguin X given the reference penguin Y, theta, and then some in-plane rotation, and then I'm going to integrate over all of them. We'll come back to that in a minute. Now, option one in cryo-EM has been called maximum cross-correlation refinement, and we'll see in a minute why that is. And in X-ray diffraction, in protein crystallography, these approaches have been called least squares refinements. And then in both fields, the second option of marginalization has been called maximum likelihood. Okay, let's discuss the maximum cross-correlation approach first. It's, in both fields, was the first to have been implemented, perhaps because it's slightly more intuitive to start thinking of. So if we start from some initial guess of our penguin, and we'll get to that, how that happens in real life, but imagine we have some kind of blurry estimate of how a penguin would look like, and we have one of our noisy experimental penguin images. Then what we need to do is calculate some kind of figure of merit to say how good a fit is the image in this orientation compared to the reference. And for that, we'll use this cross-correlation term. And I thought I'd do that on the whiteboard. So we have one blurry image of how a penguin should look like, and we have one noisy image that is our experimental penguin. And it's so noisy I can't even see it in this one, okay, but it's there. Now, as already, I think Paula explained, an image is just a two-dimensional array of values of the intensity. If it's a grayscale image, every pixel has one value, and then you build up the image by just having all those pixels next to each other. So white could be high values and black could be low values typically, okay? Now, that means we have an image A here, which is the reference, and every pixel value is then called, I'll call it lowercase a with a subscript j, where j is the index of the pixel. And then it goes from pixel 1, 2, 3, all the way to however many pixels, capital J, there are in the image. And the same happens for image X. Now, if you want to express how similar these images are, because we want to find, what we're going to do is rotate the noisy one around and see when does the rotated image look most like the reference image. That's the thing that we're going to do. Now, one way to do that, say, oh, they look most like each other, is when the difference between the two images is smallest. So what you could do for every pixel AJ in the reference image, you could subtract a pixel in the experimental image. Now, and then what you could do is take the square of that because you don't care whether they're slightly too big or slightly too large in the experimental image compared to the reference. You just want to minimize the square difference. You get rid of that. Okay. Now that would be for 1 pixel J. So if you want to express for the entire image A and the entire image X, you could just do a summation over all the images, over all the pixels J in the image. So this is just a figure of merit that you could try to minimize when you rotate these images. Now in practice, what people do is this cross-correlation, and I'm just going to use some high school math. If you write this out, this will be something like I hope you remember from high school. And what we have here is a term that only depends on image A. This is a summation over all the pixels in image A of the power of the pixels, and the same for X. Now these two terms do not depend at all on how much image A resembles image X. The only thing that depends in this equation that depends on how much A is similar to X is this term, and this is called the cross product. So, and this is the main part actually of the cross correlation coefficient. There's some other things going on to make it invariant to scale and so on, but we won't go into detail. So if you do maximum cross correlation coefficients, then we actually want to maximize the cross product. So if that's maximal, then because the minus here, this term will be minimum, and we're doing, so that's where maximum cross correlation becomes the same as least squares, because if you maximize the cross product, then the square difference becomes the smallest. So that's just a very simple calculation that you could program yourself. You could just run over all the pixels and do this calculation. And then what we're going to do is take the image and calculate that cross-correlation for this relative orientation. Won't be too great, because as you can see, the penguin is not really similar. The experimental image is not really similar to our initial guess. And we can just keep rotating it around and calculate that same value. That might be the one that fits best. And you can then plot it. So we plot on the x-axis rotation and our cross-correlation on the y-axis. And then the point where the cross-correlation is largest, the square difference will be smallest. And that's where those two images fit best. Now that kind of intuitively makes sense, because we have these images in the micrograph, and we've picked up this penguin, and the physics behind the whole thing, it is one penguin image in a given orientation which we compare to the reference image. We just have to find which orientation it is. So this is our attempt at finding that orientation. Now, once we have that for the first image, we go through our thousands of images, and we determine the best orientation for all of them. So that's illustrated here. We are going to use our initial guess of the penguin to find the best cross-correlation coefficient for all these images, and then we have this set of kind of aligned images. Again, there are the same type of errors that I mentioned earlier with three-dimensional Jan in these arrows, because the estimate that we have of the penguin is not perfect. So again, we have kind of a non-random type of error in the orientations, which will to some extent make this bad penguin come up, but also will have some of the true signal averaging out. So this one will be better than that one. and we can again do the exact same iteration that we did before with Jan. So this is the exact same algorithm. Rather than going into 3D to do a reconstruction, I'm just staying in 2D to do averaging. And then hopefully next time round, the penguin is now much better, and now the images are, the errors in these alignments get much smaller, and then hopefully after a while, I get to the estimate of the true underlying signal. Good. Now, the maximum likelihood approach is very closely related to this, and we start again off by our initial estimate of the underlying signal. So there's some blurry estimate of a penguin, and we have our experimental image in any kind of orientation. Now we're going to calculate a probability that of observing the image in whatever orientation it is in, given the estimate of the penguin that we have, and an estimate for the amount of noise that there is in the image. And that works like this. The underlying data model is that our experimental image is the summation of the actual true signal plus a noise image. And the noise, we're going to assume that it's Gaussian distributed with a mean of 0 and a given standard deviation, and then we normalize these images so we can assume that the standard deviation is 1 in them. Now, if we assume that is the case, then we can calculate something which is the probability of observing an image X given the reference image and giving any kind of relative orientation of them and the amount of noise. We can then calculate as follows. We do that as a multiplication over all the pixels. So if we assume that the noise in every pixel is completely independent from all the other pixels, then we can multiply through probabilities. So I'm going to put a big multiplication over all the pixels in the image. And we're going to do the probability of each individual pixel, xj, and then that was aj, and then given some relative rotation and sigma. Now the rotation could be here a rotation matrix. So we have the experimental images are all a rotated version of the penguin, and we don't know that rotation phi. Now, this term, the probability of observing one pixel in the experimental image, which assuming that the signal is aj and there is a given amount of noise, if the noise is Gaussian distributed, this will look like this. So we have the probability of xj given aj phi and sigma is now a Gaussian, which is centered at aj, and it has a standard deviation of sigma. So if the noise in the images is Gaussian distributed with a known standard deviation, and if I would assume that the real signal is A, then the probability of observing xj will be according to this Gaussian distribution. Now, I don't know high school in England, but high school in the Netherlands, you get to learn the formula for the Gaussian distribution. It's an exponent of xj minus aj squared over minus 2 sigma squared. Okay, so that is this term, and then we had the multiplication over all the pixels here. So the Gaussian is just an exponentiation of the square difference between the mean and the actual value, and you divide that by 2 times the standard deviation squared. Now, if you remember that then x times a multiplied by x times b is x times a plus b. Okay, then we're almost where I want it to be. So the probability of observing an image given the reference in that orientation, there would be some rotation there, I don't know. That would then become something like to the jth, and then exponent, and then the the multiplication here becomes an exponential inside. So what we now have is something, the probability of observing the image given this reference image is something where we have the exact same least square term that we were also optimizing in the maximum cross-correlation approach. Okay, so all these things with the Gaussian error model, etc., has led to something where the maximum is exactly at the same position, because where the cross-correlation was the highest, the least squares was the lowest, and where the least squares is the lowest, that's when x becomes a, the probability becomes again the highest. So we're still very close together, but what we're going to do with this probability is something very different, and that I'll explain on the slides again. So I kind of went over too quickly on this factor phi here, on the relative orientations of all the images. But what we're going to do with this is better explained here. So we're going to calculate this probability, which we've calculated here, for all possible orientations of this image xi relative to the reference. And so just like we had a function of the rotation versus the cross-correlation coefficient, we now have a very similar function of the rotation versus the probability of observing the image given that rotation. Now, for maximum cross-correlation, we then said, oh, what's the maximum of that function? And that will be the rotation I'm going to use. If you marginalize over all these probabilities, what you do is something very different. That is, I'm going to calculate the probability for observing the images in all these orientations, but I'm not just going to take the maximum. I'm going to calculate the average for the next iteration as a weighted average over all those different orientations for every image. So if this is the first image and the relative rotation should be something like 90 degrees, then in this orientation the probability is very low. That's why it's kind of very whitish here. This would be 45 degrees, very low. 90 degrees, I'm actually at the right orientation. The square difference with this reference image will be small and the probability will be high. That's why you can see it here. And then you rotate it back again. Perhaps when you're at the kind of upside down orientation, to some extent a penguin, if you clip off his wings and you don't look at his eyes, you can put him pretty well upside down into the reference. So that might give a reasonably good fit, which is not as good as the upside up fit, but perhaps when the noise is so large in the image, and that's a crucial point here, then it becomes kind of very difficult to find a difference. But at this noise level, it's still quite very easy, okay? But so this one has a higher probability than all these in between, but it's perhaps significantly non-zero. And I'm going to calculate the average for the next iteration now, for example, as 75% of this and 24% of this, and then the other 1% is kind of spread over all the other orientations. So rather than saying this is the right orientation, I'm going to put in I'm going to calculate the new average as a weighted assignment over all possible orientations. And that I will do not only for the first image, but for all the thousands of images that I have in my data set. And that will give an image which is hopefully better than the one we start off, very much in the same way as the cross-correlation approach, and such that we can repeat this, hopefully until convergence. Now, math then tells you that the convergence behavior of doing it that way is better than just taking the maximum. And the kind of intuitive reasoning behind it is that if you're not really sure, because there's so much noise in the images, if you're not sure whether the penguin is upside up or upside down, if you're just going to put it in where the cross-correlation function is maximum, it could be you're making a mistake just based on the noise in the image that just made it numerically slightly better least squares or maximum cross-correlation than the actual upside up. Now, in maximum likelihood, you kind of measure how much noise there is, and you say, oh, the difference between upside up and upside down kind of drowns in the noise, then more or less you'll give it 50% of the probabilities. So rather than making a mistake early on, you say, okay, I don't know early on, I'm just going to put it in with both options equally weighted. And that then converges better to the final solution. So for example, Fred Sickwood was the first to do this actual case, two-dimensional alignment of images against a single reference. And he showed that this effect of template bias, this how much does the orange poppet in Jan or the original blurry penguin persist in this iterative process, is less if you do it the maximum likelihood way than if you do it the maximum cross-correlation way. Good. So we had these two options. They're not at war with each other. They love each other very much. And I told you that they're very, very closely related. And actually, in the limit of noiseless data, then if the noise in the images is zero, then the sigma becomes zero. Then the Gaussian functions become ever narrower. And then actually, whether you just take the maximum or you're integrating over all the possibilities becomes exactly the same because they're all delta functions. So that's where I always say that if you think your data is noiseless, you should use maximum cross-correlation approaches. Anyway, I think it's quite interesting. And at the Gordon conference last week, we heard that also Sparks, this new Sphere thing around Sparks, uses maximum likelihood. Nico Grigoriev implemented maximum likelihood in FreeAlign. CryoSpark uses the same regularized likelihood target as in RELION. So it's kind of interesting to see that the whole field is moving towards these more statistical approaches, very much in line with what the crystallography field did, I guess, during the 90s. Okay, now this was only alignment of images. Let's speak about classification as well. Now, in the classification, we can do something very similar. We had this hidden parameter, which was the relative orientations of all the penguin images. And I'm going to show you already a real cryo-EM test data set. If there is now, for example, top views and side views in a cryo-EM data set, then if you want to do to average them together in 2 dimensions, you will have to separate out the top views and the side views because otherwise you get a mixed 2D class average. The way we do that inside this whole maximum likelihood framework, but you could do again the same in the maximum cross-correlation framework, is to expand this array of missing parameters, which was just the in-plane orientation before, with a new hidden parameter, which is now the classification parameter. So we're going to start with a given number of classes that the user has to decide on, and we're going to divide initially the data set into that many random subsets. And then I told you I would come back to what do you start with the initial guess of the blurry 2D two-dimensional penguin. And for cryo-EM images, it turns out that this algorithm is robust enough. We can start from initial random orientations to all the individual particles, and then we kind of get a blurry disk, which will be our initial guess of that penguin image. And in this case, this was a large T antigen projections. Now, if these are now our two two averages from random oriented, you can already see this is not completely random, but you get kind of a disk-like thing. We're going to sample all the orientations, but rather than have one reference, we now have 2, because we said there's 2 different classes in this data set. And we're going to calculate the probability of observing each image, not only for all in-plane rotations, but also for these 2 class assignments. And that means that every image in the average for the next iteration will go in with all possible relative rotations with respect to not only one reference, but to 2 references. So it could be that 60% of the relative of all the weights of this experimental image goes to the first class, and that 60% is then spread out over all the in-plane rotations, and 40% goes to this class, and it's spread out over all the relative rotations there. So it's very similar to alignment, but we just have an additional dimension to search, if you like, which is class. Okay, and then again we do this iteratively, and then what we showed is you can actually start from these kind of disk-like structures and then converge to something which makes sense. And in this case it was side views of a double hexamer or a single hexamer, and then these were different views, etc. So and that still would go on also in RELION. If you use two-dimensional class averages, you divide your initial data set into a given number of classes. Many people seem to like the value 200. I do as well. And then you just take averages in random orientations and you calculate the probabilities of all rotations and all 200 classes every iteration, and you do that for 25 iterations, hopefully converging to something which is useful. Good. That, as Rafa will also explain tomorrow, we then very often use to clean up data and to select our very best particles that we then put into a three-dimensional reconstruction. So let's have a quick look then at 3D, because we've only discussed two-dimensional alignment and classification. Now in 3D, it's again just the same thing, but expanded with another dimension. So we have, rather than what I told you, we're going to assign a top view to this particular image slightly off to the side. We are going to calculate probabilities for all the possible orientations, and now every individual experimental image will go into the 3D reconstruction of the next iteration with all the different orientations assigned, and you just calculate a weight for all of them based on the terms there, where you compare the experimental image with the reference projection in that direction. So if this is the most likely one from the top, it's slightly from the side, but because there's so much noise in the image that I can't really make out if it's slightly from the right and slightly from the left, then all of those will go in with significant probabilities. And again, the intuition is exactly the same, that if the reference is too blobby or the image is too noisy to really make out which direction it is, then it's better to avoid hard decisions and kind of back off and say, oh, I don't know, I'll just make a fuzzy decision to start with. Okay, now it's important to realize that this algorithm, which I've now gone over several times, this iterative algorithm of getting better orientations and then better averages, etc., it's a so-called expectation maximization algorithm. It is a local optimizer. So it will converge to the nearest local minimum, and if your energy landscape is complex, that means that local minimum might not be what you're actually looking for. Or in other words, if you give it a bad initial start, if your orange puppet that you start with is bad, then you might end up with something that still looks like the orange puppet, but is actually not a true reconstruction of Jan, even though it's a reconstruction only made from images of Jan. Now in 2D, I just told you, we start from random orientations and random subsets. So there is not a lot of information going in, and in practice, it's not often a problem. But in the three-dimensional case, it is more important that you start from an initial 3D model that looks somewhat like what you're going to solve. And that then, of course, raises a chicken and an egg question, because if you start your project, you don't really know what your structure looks like. So people have done all kinds of things in the past, random conical tilt reconstructions. Those are no longer really part of our course because it's not being done very much anymore. What has been very successful in the past few years is to add some sort of randomness into these kind of projection matching-like algorithms, and by kind of randomly perturbing it all the time, you can get to an algorithm which has the potential, at least, to converge to the global minimum. And one of the first people to do that was Hans Elmlund in his program called SIMPLE, a method called stochastic hill climbing, and recently very successful by Marcus Brubaker, this CryoSpark development, and they use stochastic gradient descent. And that's also actually what I've implemented in the latest version of RELION. So by introducing random perturbations to this projection matching algorithm, you kind of push the the algorithm out of local convergence minima all the time, and you can converge to the global minimum. Now, especially this stochastic gradient descent has been shown to be very robust to kind of what starting models you use. But still, if you're going to do all this, then keeping in mind that whatever model has come out of whatever method you chose could be the wrong one, and you might be stuck in a local minimum. Nowadays, with such good detectors and image quality, that will probably mean that the difference between getting stuck at a kind of a blobby reconstruction and going all the way to reconstructions where you can first see secondary structural elements and later side chains. So if you have the right model and provided your 2D class averages looked okay and you think you have good data, then you should get a high resolution reconstruction. If you kind of get stuck at low resolution reconstructions, then it might be the case that your model wasn't correct. Okay, so then there is the thing of structural heterogeneity in 3D as well, where you've kind of done 2D classification. We can also do 3D classification, and the example here is Jan with his favorite cofactor. So this is uncomplex Jan, and this is complex Jan. We now have projections of these two states of Jan in different orientations, and basically we do again the same as in the 2D multi-reference. We now have a 3D multi-reference refinement, and we make reference projections of some uncomplex Jan in all orientations and of complex Jan in all orientations, and then rather than assigning only the best orientation and class based on cross-correlation, we're going to, for every experimental image, calculate probabilities over all orientations and all classes. And then you say, oh, but I don't know, if I start doing my reconstruction, I don't know that the difference is either an uncomplexed or a complexed form of Jan, and it's actually in his right hand is the complex. So that you don't know, and that's kind of the status of the field back in 2005 or so. And again, this maximum likelihood approach to this then turned out to be the convergence properties of these algorithms allowed to again start from kind of random subsets. So this was a test case we used together with Joachim Frank, which was a ribosome, and the EFG, which they put in the sample, came out at very low threshold, and the small subunit was rather blurred. And then what you can do in this maximum likelihood approach, and RELION still uses the exact same approach, is you start from a very low-pass filtered version of this consensus structure, and then you choose how many different classes there should be, and that's something you have to do. And then you do 4 random subset of the images, and you refine these random subset each against projections of this initial consensus model, and then you get 4 models which are slightly better because they've gone through a single iteration of refinement. But the difference between them only arises from the differences in the random subsets. So, but then you can do this competitive alignment where you do all the images against the 4 different references, again doing orientational and class assignments in this probability weighted manner, and then we showed you can actually get about 6% of the images have EFG and all the rest doesn't. So that's still how RELION works as well. So in the last 10 minutes or so, I'd like to go, because all that I've explained to you now, you could kind of do in real space. I've spoken to you about real images with real space pixels and Gaussian distributions based on the values in those real space pixels. But Paula nicely introduced last week this Fourier space and how that's much more convenient to work with in many aspects of cryo-EM. And both Richard and Paula showed this image of the duck, where we have the Fourier slice theorem, and I have my own images of that. This is gamma secretase, and there's this Fourier slice theorem that says there's a 3-dimensional object. I can calculate a 3-dimensional Fourier transform, and Paula explained this very nicely. Now, what happens in the microscope is an integral along these red lines. We have a 2-dimensional projection of the 3-dimensional object, and then Paula also told us you could take the 2-dimensional Fourier transform of that projection. You can go, these are then, you can go backwards and forwards, as Paula explained. And then this projection slice theorem says that this 2-dimensional Fourier transform is this central section through the 3-dimensional transform of the original object. And then the direction is perpendicular to the direction of the original projection. Now, that then provides us with a way to do 3D reconstruction. I only talked about it in kind of fuzzy terms in real space. It's not so easy to explain the algorithms there. In Fourier space, it becomes very easy. If I know the relative orientations of many of these two-dimensional projections, I can calculate all their two-dimensional Fourier transforms and all put them back in a kind of a spider web-like fashion to the three-dimensional Fourier space, and then just do an inverse transform like that to get to a three-dimensional reconstruction. And that's what actually goes on in the vast majority of the image processing programs that are out there. So if we compare real space and Fourier space, this is a recapitulation perhaps of what Paul already told us. In real space, we have these effects of the CTF, and these effects become a convolution with the image. So the point spread function is what Paula spoke about, where each image, which was an individual point in the original image, kind of gets spread out over multiple points, and that is a mathematically expensive operation to do all the time. Whereas in the Fourier domain, you can take the Fourier transform of that point spread function, which we call the CTF, and you can then multiply terms, which is much cheaper operation. Then in real space, if you want to calculate a two-dimensional projection, you have to kind of take integrals along all the lines that go through your objects. Again, rather expensive operation. Whereas in Fourier space, you can just take a two-dimensional slice out of the three-dimensional Fourier transform, which is much cheaper. And then there is a statistical difference that we're going to exploit by setting up a noise model in the Fourier space. So we're no longer going to compare real space pixel values of the experimental image with real space pixel values of the reference image. Rather, we're going to take the Fourier transform of both, and we're going to compare Fourier space components of the reference with the Fourier space components of the experimental image. And then in order to do this multiplication over all the Fourier components now, not the real space pixels, we then have to assume there's independence between the noise terms of all the Fourier components. And that is probably a much better approximation than assuming that the real space pixels are all independent. Independent real space noise is so-called white noise, and we know that the noise in our images is not white because everything falls off at spatial frequency. Now, I won't go into too much detail, but basically we'll set up equations that look very similar to the one that I wrote down on the board, but now there is a term that actually explicitly allows for modeling the CTF by multiplication of a projection of a 3D volume, and we're going to compare that to the experimental images, and it's the same kind of Gaussian equation, but it now happens in Fourier space. Now, one thing that you can do in Fourier space is that the standard deviation of the noise, which before was just a standard deviation of the noise in all the real space pixels, now becomes standard deviation of the noise in the Fourier components. We can make that a function of the actual spatial frequency of the images. And that allows us to model for the fact that that in our, sorry, that's not very visible, in our experimental micrographs, everything becomes smaller with higher spatial frequency. So the noise drops with spatial frequency. Unfortunately, the signal drops even faster, so the signal-to-noise ratios drop. But noise is not white at all, and we'll be allowed to model that better. And by estimating the amount of noise that there is from the images themselves, and that's part of these maximum likelihood algorithms, we can then do something clever, which is Paula mentioned. You can use these low-pass and high-pass Fourier filters to kind of denoise your images and then get the best possible alignment. If you remember, she had images of Max Perutz, and then she could take away all the hairs and kind of focus only on the low spatial frequency components. Now, by estimating how much noise there is in the images at every spatial frequency, you can calculate the signal-to-noise ratio at every spatial frequency, and you can then devise optimal ways of alignment. So where you no longer have to go in and say, oh, this will be a low-pass filter and this will be the high-pass filter, and you have to tune parameters to do so, you can get an optimal filter from the data automatically. And that then leads me to the last part, which is an extension to the maximum likelihood. And that is because maximum likelihood estimators from a theoretical point are the best one can do under the assumption that you have an infinitely large amount of images. Now that's never true, even with our very expensive setup. So the bad news is that then if you do the average over a limited amount of data that is noisy, there will always be some noise remaining in the average over the noisy components. Now that then leads to a situation where there is many noisy reconstructions that all describe the data equally well, which opens the door to incorrect interpretations, because we like high spatial frequency noise and we like staring at it because we think we can see side chains, but they might not actually be there. Now the good news is you can reformulate the entire problem and you can define one which has a unique solution, and that in general is called regularization, and low-pass filtering, for example, is one kind of empirical way of doing regularization. But there is a Bayesian way to do this, and you can calculate this likelihood function that we calculated before from multiplying and summing lots of these Gaussian functions. We can extend it with the prior function, and I won't go into the details, but then we get to a new algorithm, and I'll skip over this. It calculates the three-dimensional reconstruction as now we're going to sum in the 3D Fourier transform space, we're going to sum all these two-dimensional Fourier transforms of all the images. We're going to calculate these probability-weighted assignments over all their angles, so every image goes in with all the angles. And we're going to measure how much noise there is in each of those individual images, and we're going to measure how strong the signal is in the actual reconstruction that we make out of that. And using that information, we then get a full description of the three-dimensional signal-to-noise ratio in this Fourier space. And that then leads us also to not only have these optimal filters for alignment that I just spoke about, but now we also have optimal filters on the reconstruction. So we can make the reconstruction, we can choose the one that is the least noisy out of all those possible very noisy ones. And the good news is that there is no real parameters for you then to tune this. So that takes arbitrariness and user expertise out of the equation. Now, let me just recapitulate. So alignment and classification in cryo-electron microscopy image refinement are these incomplete data problems. It would be much easier if we knew all the angles in the classes, but we don't. And the best way to deal with that is this marginalization. Calculate probabilities for all of them and then calculate probability-weighted averages rather than kind of taking the quick way home and only taking the best possible value at every iteration. The 2D and the 3D problems are extremely similar. I hope that's become clear. Whether you average things in 2D or whether you do a 3D reconstruction step inside, these iterative algorithms remain very much the same. And then Fourier space is the most convenient space to do this because we can multiply with the CTF, we can take these slices, and we can actually model the type of noise that we have in our images in a much better way. And that then leads to a formulation where you no longer need to tune all kind of parameters for low and high pass filters on both the experimental images and the reconstructions, because these kind of get learned automatically from the data for you. And that reduces the amount of user expertise that you actually need to get the best possible reconstructions out of these programs. Okay, that was it. This was just some further reading, and I thank you for your attention.